This is Kenneth Hoffman and Ray Kunze's classic text on linear algebra. Inside its pages lies a rigorous framework for understanding symmetry in mathematics. To understand symmetry in this context, we first need to recall how a general bilinear form operates. It acts like a machine that accepts two vectors as inputs and produces a single scalar value as an output, all while maintaining strict linearity in both input slots. This diagram shows a bilinear form in action. We introduce symmetry by enforcing a single rule. If you swap the inputs, feeding in beta then alpha instead of alpha then beta, the final scalar output remains exactly the same. By applying this algebraic restriction, we give the vector space a rigid geometric structure. The math now mirrors physical concepts like distance and angle, because the spatial relationship between two vectors is constant regardless of which one you measure first. This layout maps our abstract form directly into matrix mechanics. We calculate the output scalar by multiplying a row vector X transpose, a square matrix A, and a column vector Y. To see what symmetry requires of our matrix A, we write out the equation with the vectors in their original positions, and we set it equal to the equation with the vector positions reversed. Because both sides of this equation resolve to a single 1-by-1 scalar, taking the transpose of the entire left side will not change its numerical value. When we distribute that transpose operation inside the brackets, the order of the matrices reverses. We get Y transpose times A transpose times X. For this to equal our right side, the interior matrix A must equal its own transpose. The algebra proves a direct structural link. A bilinear form is symmetric if and only if the matrix representing it is a symmetric matrix. This equation defines what we call a quadratic form. Instead of evaluating two different vectors, we feed the exact same vector into both input slots of our symmetric bilinear form. Geometrically, this operation computes the squared length, or the squared magnitude, of that single vector in our space. This leads to a reverse engineering problem. If we only know the lengths of individual vectors given to us by the quadratic form, can we deduce the interaction between two entirely different vectors? We answer this by expanding the quadratic form for the sum of two vectors, alpha plus beta. Because our bilinear form is symmetric, the mixed terms combine neatly into a middle cross term, 2 times f of alpha beta. By subtracting the squared lengths of alpha and beta alone, we isolate the exact value of their interaction. This expansion is known as the polarization identity. It guarantees that the quadratic form and the symmetric bilinear form encode the exact same mathematical information. If you know the lengths, you know the geometry. This equation illustrates the diagonalization theorem. It guarantees that for any symmetric bilinear form, we can find a coordinate basis where its matrix representation D is purely diagonal, containing non-zero entries only on the main diagonal. Notice that we use a transpose matrix here, not an inverse matrix. This is a congruence transformation, which changes the basis of a coordinate form, rather than a similarity transformation, which we use for operators. Geometrically, diagonalization is the process of tilting and stretching our coordinate axes. Once aligned, all the messy cross terms between variables evaluate to 0, leaving a perfectly clean shape centered on the axes. When we restrict our field to purely real numbers, we can scale those axes further. Sylvester's law of inertia proves that we can force every entry on that diagonal to lock in as exactly +1, -1, or 0. The specific count of these positive and negative entries is invariant. By counting the positive ones and subtracting the negative ones, we calculate the form's signature, a permanent structural ID for the space. This brings us back to the familiar dot product. An inner product is simply a specialized symmetric form where every single diagonal entry normalizes to a positive one, leaving no negative or 0 dimensions. No matter how distorted or complex a symmetric bilinear form initially appears, it is built on a rigid framework of orthogonal axes. You just have to calculate the correct coordinate system to reveal them. To explore more proofs and master the mechanics of linear algebra, like this video and subscribe to the channel.